5.2a, we're going to describe a probability model for chance process. In 5.2b, we're going to use basic probability rules, including the complement and addition rule for mutually exclusive events. Let's first define a probability model. It's a description of some chance process that consists of two parts. We're first going to have the sample space, and you may see that defined by the capital letter S, and then you're going to have a probability for each outcome. Okay, now what's a sample space? Well, a sample space is just a set of all possible outcomes that could happen. Now let's look at this example. Imagine flipping a fair coin 3 times. Describe the probability of this chance process. So again, the trick thing that I like to do to figure out how many should be in this sample space is to imagine I have coin 1, coin 2, and coin 3. And I think about the probability of flipping on coin 1. On coin 1, there's 2 outcomes. And then on coin 2, there's 2 outcomes. Coin 3, there's 2 outcomes. Heads or tails for each. What I'm going to do is flip coin 1 and coin 2 and coin 3. And a lot of the times in probability theory means multiply. So if you multiply these, you can get a nice concept that there's going to be 8 elements in this sample space. So to describe the probability model, we should list the sample space basically. Well, can you write down all 8 outcomes? Sure. First one might be, there are 8 outcomes. The first one, heads, heads, heads. How about heads, heads, tails? Heads, tails, heads. Heads, tails, tails. Tails, tails, tails. Tails, tails, heads. Tails, heads, tails. And tails, heads, heads. I think we got all 8 of them. So that would be what the chance process looks like. And what we could say about that is this. Since the coin is fair, each of the 8 outcomes will be equally likely and have the probability of 1/8. That would be describing the probability model for this scenario. Okay, let's answer a question. Use this sample space that we just did to find the probability of getting at least 1 head in 3 flips. Well, that's easy enough. Just look at your sample space. Of getting at least 1 head in 3 flips, that would include this and this one. That's at least 1. This is at least 1. That's at least 1. That's at least 1. And that's at least 1. So the probability of this happening would be 7 out of 8. Do keep in mind, I mentioned earlier, in probability theory, fractions do not have to be simplified. Obviously, we can't simplify 7/8, but if we had 6/8, for example, you would not have to actually simplify that, but you could if you wanted to. Now, asked to define an event. An event is any collection of outcomes from some chance process and the subset of the sample space. It is usually designated by capital letters. So you might see some shorthand. Maybe they're going to say, let E stand for the event of rolling an odd on 1 die. This would be the event, and we could find the probability of rolling an odd on 1 die. By the way, that would be 3 out of 6. Okay, let's talk about complement. What a complement is the probability that an event does not occur, and then you're going to actually minus it from 1. And that'll give you the probability that the event does occur. So this is some math shorthand. The P means probability. This is of event A. What is the probability that you get the complement of event A? Well, if you take the whole set, or 100, and you subtract event A from it, this means not event A. So do know that this right here means not A. Complement refers to not. It basically means it's not going to happen. So to find that not A is going to happen, just take 1 minus A actually happening, and you will get the answer. Now, mutually exclusive or disjoint mean the same thing. Let's define that. It is when 2 events have no outcomes in common, so you can never have them occur together. 2 events that I think are pretty straightforward. What if event A represented that you were a guy and event B was you were going to have a baby? What's the probability you're a guy and you have a baby? 0. It's never going to happen. So the probability of 2 events happening, if they're mutually exclusive or disjoint, would actually be 0. And I'm going to write that more formally. So what you could write for what mutually exclusive might look like is if it said the probability of A and B both happening. In this case, it would be 0 if they are mutually exclusive events. We are going to talk about when they're not mutually exclusive, you can actually get an answer. But for now, mutually exclusive, they can never happen together. So be careful though, because the and one is going to be 0, you could still do or. In probability theory, when you hear the word or means to add. So in this case, could I find the probability of A or B? Sure. I would say, what is the probability I'm a guy? And then I would add to it, what's the probability that I'm going to have a baby? Well, if I'm just talking to guys, this would have a number and this would actually be 0, but we could actually compute the answer. Now, it's important we highlight some basic rules of probability. The first one we've already touched on. The probability of an event is any number between 0 and 1. Can't be lower, can't exceed it, but it could be 0 or 1. All possible outcomes together must have a probability whose sum is 1. So if you're doing that or probability, which means to add probabilities together, if you get greater than 1 means you have an issue and you have to end up subtracting something out. We'll talk about that in a bit. Step 3, if all outcomes in a sample space are equally likely, then you can say the probability that event A occurs can be found by doing this shorthand. The probability of event A is the number of outcomes for A to happen over the total number in the sample space. We've already done this formula. 4 is the complement theorem, which says not A. How do you find not A? Well, A plus not A would equal 1. A good example, what if event A meant I'm a guy? Well, if event A is that I'm a guy, if you add to it what means not a guy, well, it means you're a girl. So the guys plus the girls would equal the whole of 1. And then recall mutually exclusive, or the word disjoint, means two events have nothing in common. Therefore, their probability would be 0 if you found the probability of A and B together. Here we have a probability distribution, and it shows here. They randomly select a student who took the 2010 AP Stats exam, record the student's score. Here's the probability model. Well, you're going to get a 1, 2, 3, 4, or 5 on the AP exam. Those are all the possible outcomes. Here are the probabilities associated in the 2010 exam of where you would have lied. Part A wants to say, show this as a legitimate probability model. Well, how could you do that? Well, if this table here shows us every possible scenario, it means these probabilities have to add back to the number 1. So what we could say is all of the probabilities are between 0 and 1, so that's legit, and the sum of the probabilities is 1. So therefore, this is a legitimate probability model. The next one, find the probability that the chosen student scored 3 or better. Okay, this is not meant to be a hard question. A 3 or better are those right there. How are you going to find those? All you need to do is the addition rule. What's the probability you got a 3 or a 4 or a 5? Again, in probability theory, when you hear or, it means add. So I'm going to take the probability of a 3, of the 4, and of the 5, and we add it up, and we got it. Now, there's actually a different way you could do this problem. If you wanted to, you could go ahead and you could use the complement rule and the addition rule together. So if you get a 3 or higher, the complement of that would be, how about doing 1 minus a 2 or less? Okay, so 1 minus a 2 or less, all we're going to do is we're going to take these 2 here and subtract it from 1, and lo and behold, that's going to give us the same answer, obviously. Part C, find the probability that the chosen students didn't get a 1. Well, this is a great example, folks, of a complement event. Another way of saying you didn't get a 1 is that you got a 2, 3, 4, or 5. So again, there's a variety of ways you could actually do this problem. But I'm going to keep it as you didn't get a 1. So to write this out, the probability you didn't get a 1, that equals 1 minus the probability I did get a 1. Well, that's 22.3%. So take that minus 1 minus that, and we're going to get the answer is 0.773. Now, again, this is not the only way to have done this problem. I could have just added all 4 of these up if I preferred to. Check your understanding of the material. Here we have 2 events. We have event A, which is a person has a cholesterol level of 240 or above. Event B, a person has a cholesterol level of 200 to 239. Okay. According to the American Heart Association, the probability of A is 16%. That's this. Probability of B is 29%. Explain why the events A and B are considered mutually exclusive. Well, can I have a cholesterol of 240 and higher and at the same time have a cholesterol of 200 to 239? Well, you can't. That doesn't make sense. A person cannot have a cholesterol level of both 240 plus and between 200 to 239 at the same time. Therefore, these events are mutually exclusive and have nothing in common. So if they had asked me to find the probability of A and B, it would be 0. Okay, explain in plain language what the event A or B means. Well, in A or B means you either have this cholesterol level or that. Remember, or probability means to add. So in plain English, a person having either the level of 240 plus or between 200 and 239. How do you find that? You do probability of A plus the probability of B. If they asked us for the numerical value, we would just add these 2 together and we would get that it's 45%. Okay. Part 3. If C is the event that a person chosen has a normal cholesterol level, which means below 200, what is the probability of C? Well, the probability of C, which is getting below 200, we could do the complement. We could say that's the same as 1 minus the probability of A or B. Well, the probability of A or B, if we add those 2 together again, is going to be 45. So let's do 1 minus 45, or 0.45, and that's going to give us a probability of 55%. Let's look at a flipping coin example. You flip 3 coins at one time, and then find the probability of each. So remember, if you do 3 coins, that means coin 1, 2, and 3 are all going to land by each other at the same time. That would be heads or tails, heads or tails, heads or tails. So 2, 2, and 2. There's 8 outcomes. So I'm going to be looking for 8 outcomes, by the way. Question for you. Is that different than if we flipped 1 coin 3 times? What if I came in and flipped the coin once, recorded it, flipped a coin twice and recorded it, and flipped a coin a 3rd time and recorded it? Is that different by doing 1 at a time 3 times or all 3 at once? They actually are the same type of scenario, so don't let that actually fool you in the wording. Okay, I'm going to go ahead and actually write out the sample space, by the way, for these 3 coins. When I do that, here's all 8 outcomes, and I know I have them all. They want us to do for event A is define the probability of flipping 2 or more heads on the coin. So all I have to do in that case is find all of the scenarios that have 2 or more heads. We've got that, this one here, and I think that's going to be it. If you count them, we're going to have 4 out of 8, or you could say 1/2. Part B, define the probability of flipping no heads on a coin. No heads, by the way, what you could actually do is either count up how many of them have no heads. That's actually not too hard. It would be this one right here. And therefore, we're going to have the answer be 1/8. The last one, define the probability of flipping at least 1 head on a coin. Folks, at least 1 head on a coin means I can't have all tails. So you could actually piggyback off of this answer here and do the complement. You could do 1 minus 1/8, or you could just count them all up. In this case, you're going to get the answer is 7/8. Let's wrap this up with a dice example. We're rolling 2 dice. Again, remember die 1, die 2. That would be 6 and 6 outcomes, so 36 in total. Here are all 36. Be cautious. You're never really going to be given the picture of all 36 dice, so don't get too comfortable with this. But again, there's 36 outcomes in the full sample space. They want us to find the probability of rolling a sum of 3. Well, a sum of 3 on here is 2 and 1 or 1 and 2. And if you look at that, where it means we have 2 out of 36, which could also be simplified to 1/8. Do make sure to read the Schoology questions carefully on the quizzes. I do have to put the correct answer in there, and sometimes I will ask you specifically for the simplified version. Now let's find the probability of rolling a sum of 7. So if we take a look at that, we have 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, and 1 and 6. So there we're going to have 6 out of 36, which could simplify to 1/6. Part C, rolling a sum of 3 or 7. What's the probability? Remember here, we're going to do the addition rule. So in this case, what I want to find is the probability. I'm going to put the sum is equal to 3, or the probability that the sum is equal to 7. Now, we already found those. We know the sum of 3, I'm going to keep that as 2 out of 36. The sum of 7 is 6 out of 36. This will simplify to 8 out of 36. Now, I do want to make note, how would you fill in these two spaces? These two events right here, sum of 3 and sum of 7, you're going to notice on the diagram they never overlap, which means they have nothing in common. So I can say this one is the addition rule for mutually exclusive events. Do make note, though, as we get more into the notes, there's times when you have to do or probabilities where they are not mutually exclusive, and we'll end up adjusting this formula by adding a third component to it.